So we're going to continue on talking about ionic compounds and specifically predicting the charges of the cations and anions. So this skill is specifically uh, talking about ionic compounds because ionic compounds contain ions, cations, and anions, and those species have charges. So essentially, with predicting charges, we need to figure out how many electrons are either gained or lost in each of the atoms. And essentially, remember, the atom's goal is to get a noble gas configuration or full valence shell. So always keep that in mind. Our handy periodic table is going to help us predict the charges for the majority of the elements. So here are some typical ionic charges for different elements. So take a look here. We have the group number. These are organized by group number. And remember, group number also tells us number of valence electrons in the neutral atom. So if, like, for example, group 1A, all these elements, lithium, sodium, and potassium, in their neutral state only have one valence electron. So it's quite easy for just one electron to lose, each of those atoms to lose one electron to have an overall +1 charge. And same thing for group 2A and 3A. Those extra valence electrons will just be lost, and then you will have an overall either 2+ or 3+ cation. Versus you look at the nonmetals over on this side, these are groups 5A, 6A, and 7A. These have 5, 6, and 7 valence electrons respectively, and instead of losing electrons, these elements will more likely gain electrons to achieve that full valence shell, that noble gas configuration. So for example, nitrogen, which is in group 5A, there are 5 steps to the closest neon. So nitrogen will most likely gain 3 electrons to achieve that full octet, to have 8 valence electrons. And so that is how we predict the charges. But I'll go through all the rules, but for the majority of elements, the periodic table is a wonderful resource for you to predict those charges. Yeah, so I have it right here. So remember, the goal for predicting charges of monoatomic atoms to predict their ions our goal is to see how many steps is it to the closest noble gas. Typically, metals on this side lose electrons. Metals lose electrons, while nonmetals gain electrons. And that is due to, nonmetals being closer, there are less steps to gain electrons to achieve that noble gas configuration, where metals, it's less steps to lose electrons to get to the period before that noble gas configuration. All right, so I'll just summarize the rules here. So metals, we already talked about this, that if there's 1, 2, or 3 valence electrons, those metals tend to lose all of those valence electrons to achieve a noble gas configuration. So essentially for groups 1, 2, and 3, that is the charge of the positive cation that is produced. So just remember, these are metals that are on the left side of the periodic table. While for nonmetals, we already talked about this. Nonmetals are on the right side of the periodic table. They have either 5, 6, or 7 valence electrons, and they tend to gain electrons to get to that magical number of 8. And so essentially to predict the charge for anions, it'll typically be the group number minus 8, which is, our octet, our full valence shell, and that will be the charge that is on that specific atom. So for example, if we look at oxygen is group 6A, so 6 minus 8 equals -2. So if oxygen were to form an ion, it will most likely be an oxygen 2- anion. All right, so we talked about metals, nonmetals, and then finally, if you've been keeping track of all the groups that I've been talking about, we haven't said anything about group 4A yet. And so 4A includes carbon, carbon being our nonmetal. So carbon can become either a 4 plus cation or 4 minus anion. That is because it can either gain 4 electrons or lose 4 electrons. And, for 4 steps in either direction, one is not favored over the other. And so this makes carbon a bit special. And we will talk more about carbon when we get to compounds and molecular, sorry, not compounds, but covalent compounds. All right, so carbon typically is not involved in ionic compounds. Carbon's typically involved in covalent compounds, and that is due to carbon doesn't really exist as either of these. It can exist as either of these charges, and it's not as distinct like in all of our other examples for metals and nonmetals involved in ionic compounds. So here is just kind of like a summary of everything that I just said. So here we have metals on the left side of this table, and this is just showing you based upon the group number, to get to the nearest noble gas, it's the least amount of steps. So for these guys, sodium, magnesium, aluminum, sodium only needs to lose 1 electron to get to neon. Magnesium needs to lose 2 electrons to get to neon. Aluminum, 3 electrons to get to neon. And that is how we predict those charges. What is the least number of steps to get to the nearest noble gas? And again, metals lose valence electrons. They are typically cations in an ionic form, while nonmetals, it's the same deal, but now instead of losing electrons, we're gaining electrons to get to the nearest noble gas. And so you see that here, nitrogen, oxygen, fluorine. If we want to make ion forms from the neutral atoms there, nitrogen, it's in group 5A. It needs to gain 3 electrons to get to that magical number of 8, where the closest noble gas would be neon. Oxygen needs to gain 2. Fluorine needs to gain 1. And again, always be looking at those, always be looking at the number of valence electrons or the group number for these representative elements. All right, so I've done enough talking. Let's actually put together some of these charged cations and anions and put them together into actual chemical formulas. Because, in lab, you typically won't go to the shelf and grab just sodium ions. It has to exist as a compound, an ionic compound. So instead of just grabbing, sodium cation off the shelf, we grab a compound, an ionic compound that contains sodium. So in this example, we have sodium cation and chloride anion. How that exists as a compound, the goal here when creating or putting together compounds from cations and anions is to get a net charge of 0 for that completed compound. So yeah, in order to determine the chemical formula, you need to have a net charge of 0 in the formula. So for sodium cation and chloride anion, it's quite straightforward. If you look at the charges here, sodium has a +1 charge, chloride has a -1 charge. So if I put together 1 sodium and 1 chloride, we just need to have 1 of each, 1 cation, 1 anion, and then that will equal 0 because, +1 plus -1 equals 0. So the completed chemical formula for an ionic compound containing sodium and chloride will be sodium chloride. So see, I didn't put the 1s there. All right, so just writing the chemical symbol here implies that there's 1 of each atom. So let's look at other examples where it's not just a 1-to-1 ratio. Remember, our goal is to get to a net charge of 0. So here we have potassium and oxygen. So let's think about, okay, how many potassiums, how many oxygens do we need to cancel all those charges for it to equal 0? So, you can think, okay, oxygen is -2, all right, and potassium is +1. So if we added this up right now, there would still be an overall -1 charge if we just had one potassium cation and one oxygen anion. So we need to gain a second potassium. All right, so if there's 2 + 1 potassiums, that can cancel out with a -2 charge on oxygen. So our formula will be K2O, where this subscript means that there are 2 potassiums have to be present to cancel out the charge of an oxide. So some folks in high school, you might have learned how to do it this way. So if we have a potassium and an oxygen 2- coming together, what you might have learned in high school is you take the charges and you switch them. So that +1, or that potassium plus, there's an implied 1 there. So you just like switch the charges and that becomes the subscript. So there would be a K2 and an O1. But we don't include ones, so this would actually be K2O. So that's another way that you can do it, and you always want to simplify the formula as much as you can. So if I had like something like barium 2 plus and oxygen 2-, so if we did that same deal and just switched the charges and made them the opposite subscript, this would be barium 2, oxygen 2, but we can simplify that. So if there's 2 bariums for every 2 oxygens, that also means that there's 1 barium for every 1 oxygen. So you can actually just write it like this: barium oxide. So that's an example, another example of showing how to predict how cations and anions come together to form neutral compounds for ionic compounds. Okay, let's just keep going. Okay, so calcium 2 plus, chloride minus. So again, the goal is to cancel charges. So if you change the subscripts here, this compound involving calcium and chlorine to make an ionic compound will be calcium chloride, and there has to be 2 chlorides because there's a -1 charge here, there's a 2 plus charge here, so essentially you need 2 chlorines present. So then all the chlorines, the 2 chlorines here, has an overall 2- charge, and that can cancel out our calcium. And finally, aluminum and oxygen. So in this case, the numbers are not as friendly as like, the number 1 or -1. So here the tip with, just changing the charges to become subscripts, that is a nice way to do this problem. So oxygen has a 2- charge, so I'm going to put that 2 as a subscript for aluminum. So this will be 2 aluminums, and then there'll be 3 oxygens. I just took the charge from aluminum and made that the subscript on oxygen. But you can also check your work here. So if we check our work, there's 2 aluminums. Each aluminum has a 3+ charge. So this aluminum, there's 2 aluminums, and it has a 3+ charge. So all the cations equals +6. Oxygen, on the other hand, there's 3 oxygens, and each of them have a -2 charge. And so all of the anions has an overall -6 charge. So you see all the anions cancels out with all of the charge of the cations. So that is a neat way that you can check your work for determining chemical formula from ionic species. So our answer here is aluminum 2, oxygen 3. Okay. So I wrote all those chemical formulas, so I'll just summarize those rules that I just that I kind of used. So the rules for writing chemical formulas is you always put the cation first. The cation or the metal always goes first. Then you don't put, once you put the compound together from the cations and anions, you don't show the charges anymore. So remember, the entire compound is now neutral, so we don't show the charges on the individual ions. And so that's what you see here. See how, after combining these ions, I wrote the neutral compound, there are no charges. And then the number of ions is listed as the subscript on each element symbol. Keep in mind that the compound needs to be overall neutral or a net charge of 0. And then finally, if the number of ions is 1, if you're using 1 as a subscript, it's implied, so you don't have to write a 1 subscript. Do not write 1 as a subscript. All right, so for sodium chloride, we would not write sodium 1, chlorine 1. Those 1s are implied, so you would actually just write it sodium chloride. All right, so we went over all the rules for writing chemical formulas and predicting charges. So let's put those two skills together and do some practice problems that are more realistic to how I would assess you on an exam. So a question that you could see on an exam would be, what compound can be formed from the reaction between aluminum and bromine? So the first thing that you should identify is this an ionic compound? So I'll just write the steps in the corner here. So ask yourself, is it ionic? So if we're combining aluminum and bromine, remember ionic compounds have a metal and a nonmetal. So in this case, we do. Aluminum's a metal, bromine is a nonmetal. So in this case, yes, it is ionic. Then our second step would be to predict the charges for all the species involved. All right, so aluminum, usually what helps me is I ask myself, okay, what's the group number for each of these? So for aluminum, it's 3A, and bromine, it's 7A. So aluminum is a metal. It's most likely going to lose its valence shell electrons. So aluminum, most likely as an ion, will be aluminum 3+, because it's going to lose those 3 valence electrons. Bromine, on the other hand, it's a nonmetal. It's in group 7A. It's less steps to just gain 1 electrons and get to that magical number of 8. So bromine as a ion will most likely be bromine minus, or bromide. All right, so we predicted the charges. And then finally, the last step is just to combine ions to make a neutral or, zero charge compound. Zero charge compound. All right, so now we just have to see, okay, how can we combine these two ions to have a net zero charge? So, if we want to do our subscript charge to subscript trick, this is like -1, that 1 is implied. So we just switch the charges and make those the opposite subscript. So this would be, aluminum 1 Br3, where the charge on the aluminum 3 becomes the subscript on bromine. But remember, we don't write the 1s. So this would be 1 aluminum, 3 bromides. And we can go ahead and check our work. Aluminum has a charge of +3. There's only 1 of them. So from all of the cations, it's +3. There's 3 bromides, and each of them has a -1 charge. So that equals -3. And you see from all the anions, that cancels the charge of all the cations. So this is more of a realistic question I would ask you, because it tests a lot of things. It's, can you identify an ionic compound? Can you predict charges from neutral atoms off the periodic table? And then finally, can you predict how a compound is formed from different charged atoms? All right, let's do one more. So let's go through the same steps for this one. What compound is formed from the reaction between strontium and nitrogen? So first ask yourself, is it ionic? Well, yes, it is. We've only learned about ionic compounds so far. So yes, it's ionic because strontium is a metal. It's an alkaline earth metal, right there. All right. And then nitrogen is a nonmetal. So yes, it is ionic. Next step is to predict charges. So again, I like to just write the group number to remind myself the number of valence electrons. So strontium is group 2A, nitrogen is group 5A. All right, so this will help us predict charges. Metals lose electrons, so strontium as an ion will most likely be strontium 2+, and nitrogen will most likely be nitrogen 3-. All right, so then those are the most likely ions. from those two elements. So now our last step is to combine them to make a neutral compound. So I'm going to put that 2 charge on strontium as a subscript there. Nitrogen, put a 3 in front of strontium. So our final chemical formula for strontium and nitrogen will be strontium 3, nitrogen 2. We can check our work. There are 3 strontiums. Each of them has a +2 charge. So from the cations, there's an overall 6 charge. While nitrogen, there's 2 of them. And each nitrogen has a -3 charge. And so the overall charge on the anions is -6. So you see those two, the cations and anions, cancel one another out with the indicated subscripts that we have here. All right, so let's keep going on with some more practice problems. All right, so here, select the correct formula for each of the following ionic compounds. So here, I've actually given you the charges. All right, so you're essentially just applying that last step of our 3 steps that we had before. Can you put together an ionic compound where all the charges cancel one another? So I'm just going to give you the answers here. All right, since I've given you enough examples of how to combine charges. The lithium cation in this first one, it's +1. Oxygen has -2. So we need 2 lithiums. So our answer would be 2 here. How do you combine aluminum and chloride? I think we did this example, but we need 3 chlorines or chlorides. And then our last one, magnesium and nitrogen. Again, if you just switch the charges and make them opposite subscripts, then you will get your answer. And so there is our answer. Number 3 is our answer between magnesium and nitrogen. There has to be 3 magnesiums, 2 nitrogens. So before we get on to naming ionic compounds, let's make sure that we can recognize ionic compounds when we are given a bunch of them in a list. This is the first step in the 3 steps that I talked about. First it's, is it ionic? Then predict the charge, then combine it to make a neutral compound. So let's make sure that we can recognize ionic compounds, because this will help us with naming, because the rules for naming ionic compounds is different than for covalent compounds. So if you remember that first slide, we said ionic compounds always contain a metal and a nonmetal. So this is how we recognize ionic compounds. Is there a metal present that's connected to a nonmetal? So here, all we have to do is identify the different elements involved in these different compounds. So this question is asking which are ionic, so let's just find where the metals are at. So if I go through all of these, no, I think it's on the next slide. Yes, so let's go through all of them. Aluminum is a metal, it's group 3A, and then sulfur is a nonmetal. So this would be ionic. Hydrogen, although it's in group 1A, it is one of the exceptions, and so hydrogen is a nonmetal. Oxygen is also a nonmetal, so this is not ionic. And not ionic, we will learn later, means covalent. Potassium and fluorine. So potassium is a group 1A metal. Fluorine is a nonmetal. So this is ionic. Fantastic. Carbon is a nonmetal. It's in group 4A. And oxygen is also a nonmetal. So CO2 is not ionic. All right. So we're going to look at naming ionic compounds. So these two, the aluminum and the potassium compounds, those were our ionic compounds. So this is super important when trying to name things. Being able to identify ionic compounds from a given chemical formula is super important, because there are different rules for ionic compound naming versus covalent compound naming. And so the rules for this naming is in this naming compounds handout that I've uploaded. So you see here, here's the handout, and on the first page of the handout, there are two headings. We have covalent compounds, and then we have ionic compounds. So you see that there are different rules associated with each of them. So let's just ignore this first one for now because we haven't gotten there. But if we look at ionic compound naming, here are all the rules that go along with ionic compound naming. And with ionic compounds, they have their own set of names for cations and anions, which are on the second page here. So understand, because these are cations and anions, that these names only apply to ionic compounds, because ionic compounds contain cations and anions. So use this handout as a reference sheet. So let's go back to the lecture. All right. So yeah, rules for naming, it's all summarized in the handout, but we'll still go through the different steps. So typically, the biggest rules is you always name the metal first. And it's just like how we write chemical formulas. You put the metal first and then the nonmetal. So when you write out the full name, you also say the metal first. It's just exactly how you read it. And then the anion usually has some type of suffix attached to it. And I'll talk about that in the coming slides. So naming ionic compounds, we name the cation first, then the anion. So with cations, it's quite straightforward. Cations, essentially the ion just takes the element name. If we're just talking about the ion, you'll call it an ion. So we have a calcium atom here, but if it's in its cation form, so it's a 2+ charge, we will call it a calcium ion. So that's how we differentiate the neutral species and the charged species. So you tack on the word ion on it. All right. And so again, predicting the charges of the different representative elements, that comes from the group number. And we already talked about predicting charges. So the cations in groups 1, 2, and 3 are quite straightforward to predict their charge and to name. Where things get a little different is the elements or the cations that don't fall in these representative groups 1, 2, and 3, namely the transition metals. So transition metals can actually exist in more than one charge. So they didn't really fall neatly into our predicting the charge charts that we were talking about in previous slides. And this is also why we give them the name transition metal, because they can exist in more than one charge. And so since it's not easy to predict the charges on transition metals, we typically have to denote the charge of that particular atom in that compound. And we do this, we denote the charge or tell the reader what the charge is using a Roman numeral. So for example, if we have a copper transition metal cation, it can exist as a +1 or a +2 charge. So when talking about the ions that form from the neutral compound once it loses electrons, we can call copper that lost only one electron, we call this a copper Roman numeral 1 in parentheses ion. So how this differs from our previous, groups 1, 2, and 3 elements is that we have to include this Roman numeral to tell us what the charge is, because it's not as easy to predict for transition metals. And then the other example here, copper 2+, so copper can also lose 2 electrons in certain compounds. So this copper we call copper parentheses Roman numeral 2 ion. So those are the other types of ions, and so many of the transition metals have this denoting the charge in parentheses, but there are some exceptions, and I'll show you. Finally, another type of cation that we can have is polyatomic, and the only polyatomic cation that we will deal with here is ammonium, and so you'll just have to memorize this, that ammonium is NH4, and it has an overall charge of 1. It's a +1 cation. And we call this an ammonium cation. So you won't find ammonium on the periodic table. Ammonium is polyatomic, meaning that there's more than one atom there, that there's nitrogen and 4 hydrogens, but overall, that species has a +1 charge. All right. So, I said that some transition metals can have variable charges. There are also other transition metals that have fixed charges. And in these 3 examples, there's no Roman numeral necessary. So our fixed charge transition metals are zinc, silver, and cadmium. And so these are the charges you will not find zinc in another type of charge. You won't find zinc 1 plus, although it is a transition metal. Each of these ions have a fixed charge. So we would just call a zinc 2 plus just zinc ion, or silver plus silver ion, or cadmium 2 plus cadmium ion. And then finally, mercury is like our last kind of wild card. Mercury can have two different ion forms. We can have a mercury 2 plus, and then we can also have a polyatomic mercury where two mercuries come together to make mercury 2. Both of them have to exist together, 2 plus, and so we have to use the Roman numeral system here. All right, so this first mercury example, you just take it from its charge, mercury 2 plus, so this is a mercury 2 ion. And this second one, because there are two mercury atoms sharing a 2 plus charge, we actually call this mercury 1 ion. So this mercury 1 ion does not actually look like mercury 1, mercury like plus 1. There's actually two of them stuck together. And so there is our exception with mercury. So all of those naming rules and naming of cations are outlined in that handout, in the second page of the handout. So here are all the common cations and how you'll name them. So it's all really summarized right here. So we talked about cations. Let's now, oh, there are the fixed charge metals, sorry. So fixed charge cations are group 1A, 2A, 3A, and then 3 of the transition metals. Those 3 are also fixed, so they do not need Roman numerals. No Roman numerals. While all other transition metals need Roman numerals. All right, now we will talk about anions. So anions are a little bit different than cations, and so we can't just straight take the name from the periodic table. We'll do the simplest example first. Let's talk about monoatomic anions, meaning that there's just one atom present, like, just one bromine or one sulfur, one nitrogen. So how naming for anions works is that we take the name of the element, we just take the base of the word, and then we add IDE to the name. So for example, bromine is the neutral atom. So if I'm just talking about the element bromine, it's just Br, versus the ionic form of bromine. If it gains an electron, it becomes bromide. So see how I took away the ene part and replaced it with ide. So we don't just tack on ide, we have to replace the ending with ide. And you've probably heard me kind of say like chlorine versus chloride, or oxygen versus oxide. Those are all times where I'm trying to designate that I'm talking about the ion and not the neutral atom. So if I'm talking about bromide, in your mind, you think, okay, she's talking about the ionic form of that specific element. All right, and so some more examples for other anions. Neutral sulfur becomes, if sulfur gains 2 electrons, it becomes sulfide. So we lose the part, we gain ide, so sulfur becomes sulfide. And then finally, nitrogen becomes nitride. And then maybe some more examples. Oxygen becomes oxide. So O2 minus. All right, so anions gain that ide suffix. So all of the monoatomic anions follows this rule where we add the ide suffix. There are some other anions that don't really follow this rule, and that's just with the polyatomic anions. And there's 2 that I want you to know. So there's only 2 that you need to know. That is OH minus. So polyatomic means that there's more than one atom present, and so that OH is like fused together. It's one species, and they go together, they move around together. OH minus, so this has an overall charge. Actually, both of them have overall charges of 1. Or sorry, minus 1. We call this OH minus species hydroxide, but also see that it ends in ide, so that will help you recognize that it's an anion. And then our second polyatomic anion is Cn minus, and this is cyanide. So OH minus, hydroxide, Cn minus, cyanide. And then there are some other polyatomic anions that end in the suffix ate. And so see the handout for the rules there. There's sulfate, nitrate, chlorate. I'm not going to have you memorize the polyatomic anions. I will, on different examinations, I will give you this name and compound sheet. I don't think it's beneficial for you to memorize these, but I want you all to be able to use them, to understand how to use them. So I will always give you this second sheet here with the names and the formulas for each of the polyatomic anions and cations. But you need to know how to use them, where the formulas are here and their respective charges and their names. So, I'll give you this sheet, but I'm not going to tell you how to use it. All right. So I like this handout more than the one I have in the slide here. This is another list of a lot of different cations and polyatomic cations and anions. So see, in each of these examples, there's, at least more than one element involved in these species, and they're all charged. And each of these different polyatomic ions has a specific name associated with them. So there's a lot of them here. I'm not expecting you to memorize any of them, but you need to be able to identify that in a chemical formula, hey, this is a polyatomic anion or polyatomic ion, it has a specific name. So, I'll give you, not this specific list, but I'll give you the one in the handout. I'll give you those, but it's up to you to be able to recognize these formula and how to name them. But I'm not going to make you memorize the name of the ions and the formulas. You just need to know how to use it and identify them. So let's put together some ions, cations, and anions and form some compounds and think about naming. So here I have, like a table of a bunch of cations and a bunch of anions. So let's just go through getting those formula, putting them together as neutral compounds, and then naming it. And in this case, because they're all ions, all of these are ionic compounds. We've only learned about ionic naming thus far. So let's look at sodium and bromine first. Let's just put together the compound first, or the neutral compound. So we have a +1 and a -1. So this is so one sodium and one bromine. Let's just go down the list. So bromine and aluminum. Bromine is -1, aluminum's +3. So it's aluminum and then 3 bromines. All right, so let's go ahead and name them. So for naming, you always name the metal first, and it's just the name of the metal. So you just say sodium. Don't tack on ion, just say sodium. And then we look at our anion. Remember, our anion has ide rules. So this would be sodium bromide. I accidentally said it when naming it, but writing the formula. So let me just summarize those rules there for naming Ionic. So name metal normally, and then name the if it's a monoatomic anion. So I'll just put mono there, monoatomic, with the ide ending. Okay, so that's sodium metal, the cation we just named normally. Bromine, which is the anion, we added that ide ending. And so then aluminum here, and I'll note that both of sodium and aluminum are our fixed. These are both fixed charge, so we do not need Roman numerals. We only need Roman numerals for non-fixed charge things. So here we'll do the same thing. We'll name the metal. So this is aluminum. And then the bromine is our anion, so it becomes bromide. So you see that in those two examples, we have the bromide anion ending for both of them. It's the exact same. The only difference is the name, or the cation name. All right, what's next? Okay, sulfide is now our new anion. So how this comes together as a compound is sodium, do green, 2 sodiums and a sulfur. And then how aluminum and sulfide come together, there are two aluminums and 3 sulfurs. So that goes back to combining ions to form neutral compounds. So go back to those slides if you're not quite sure how I did that. But we're going to focus on naming here. Again, naming, start with the metal. So in this first one, it's sodium. And then our anion is sulfur, but we add that "ide" ending, so this is sodium sulfide. And then our second one here, aluminum sulfide. Great. All right, next. Our next anion is nitrogen. So how those come together as a compound would be 3 sodiums and 1 nitrogen. And then for aluminum and nitrogen, see, they're both +3, so you only need 1 of each. So it's just aluminum, 1 aluminum and 1 nitrogen. I'll show you how, if I have aluminum 3 plus and nitrogen 3 minus, you can also do the, switch the charges and the subscripts. So this would become aluminum 3, nitrogen 3, but you can simplify that. You can say there's 3 aluminums for every 3 nitrogens, but that's the same as saying there's 1 aluminum for every 1 nitrogen. So simplify. Okay, so naming. Hopefully you see the pattern here now. Sodium is our cation. We name that first, so it's sodium. And our anion is nitrogen, but we add our "ide" ending for anions, so this is sodium nitride. And then aluminum, our aluminum species is aluminum nitride. Okay, there. So we finished that whole table. So let's do some more. Okay, so now there are other ways that I can assess naming and chemical formula for ionic compounds. So in this question, it says select the correct name for each of the compounds. So we have this compound with an iron and sulfur. Iron, hopefully you can identify that this is an ionic compound because there's a metal in it. It's iron. But iron is one of our transition metals. It has a variable charge. So when naming it, we will have to have a Roman numeral to indicate the charge. But you might be asking me, Dr. N, there's no charge there. How do I know the charge? Well, we know what the charge is for sulfur. Sulfur is not a variable charge. It has a fixed charge as an anion. So we can actually use the charge here to determine what is the charge on iron. So there's more steps. This is a little bit more complex. It's asking for more skills. More skills are involved here. So the first thing I want to do, is identify, is it ionic? Yes, it is. Next, what are the charges? I know the charge for sulfur is 2 minus, so sulfur 2 minus, and there's 3 of them. So all of the anions, there's 3 sulfurs each with a 2 minus charge, so overall there is a -6 charge. So iron, I don't know the charge. I know it's positive. It has to be positive. It's a cation, it's a metal. So we'll kind of use the same thing here. So in order for this compound to be overall neutral, iron, all of the cations must have a charge of +6, right? Because this has to be neutral. So I'll set up kind of the same equation. I see that there's 2 irons. It has some unknown charge, but it has to equal +6. So I can see from that equation that this charge on iron, it must be an iron 3 plus. So I can show you the whole formula to do that. So essentially what I said is like the number of cations times the charge of the cations plus the number of anions times the charge of the anions has to equal 0. So in this case, if we go through it, the number of cations, there's 2 irons. The charge of the cation, I don't know what that is, so that's our variable, plus the number of anions, in this case it's 3 sulfurs, times the charge of the anion, which is -2, has to equal 0. So if you take this whole equation and solve for charge, you'll get that, ooh, never seen that before. If you, equals 0, right, because the compound has to be neutral. So if you solve for charge, you'll get that the charge of the cation is +3. So this is iron 3+. Okay, now we can name it because now we know the charge. So you always name the metal first. So in this case, it's iron. So all of these are iron, but it's a variable charge. So we have to indicate the charge. So it's iron Roman numeral 3. So there's our answer with Roman numeral 3. Then finally, the anion with the "ide" suffix, so it's sulfide. So our answer here is iron 3 sulfide. Okay. So if you were not paying attention to variable charges or didn't know, you might just say iron sulfide, but that would be incorrect because iron is one of our variable charge cations, and we have to essentially back calculate what is that charge on that iron depending on how many anions are there. Okay, let's do the second one. Again, this is another variable charge. First step, is it ionic? Yes, it is, because there's copper. Copper's a metal, oxygen's a nonmetal. Also, like I said, this is also variable, rats, so we have to kind of do that formula again. So we need to figure out what is the charge on copper, but thankfully oxygen is one of those fixed charged anions, so we can do this quite simply. So again, number of cations times charge of the cation plus the number of anions times the charge of the anion must equal 0. So if we go through this, the number of cations here is 1. I don't know the charge. So it's the charge of the copper plus the number of anions, which is 1. Charge of that anion is -2. That's oxygen, is a 6A element, so it will gain 2 electrons. It's +2, has to equal 0. So that means the charge on copper has to be copper 2+ in order for everything to cancel out and have a neutral compound. So our answer here will be copper 2 oxide. So that was a quite involved examples here where we had transition metals and variable charged elements within our neutral ionic formula. So let's also look at polyatomic ions and being able to identify those. So let's select the correct formula for each of these. So these are kind of tough because, the names don't indicate how much of each cation and anion there are. You have to be able to identify what the charge is and put it together, put the cations and anions together to form a neutral compound. So here, aluminum nitrate, if you weren't concerned about charges, you might just write aluminum nitrate is AlNO3. Nitrate is a polyatomic anion. It has the formula NO3. So you might just write AlNO3, but if you take apart and look at the charges of the cations and anions, you'll see that they don't cancel one another out. Aluminum has a +3 charge because it's group 3A, and nitrate has a -1 charge. So you see that as written, it is not overall neutral. So when taking the name and converting it to a chemical formula, you need to recognize, predict the charges, and put it together as a neutral compound. So I'll just, write here, aluminum as a cation is aluminum 3+, nitrate is NO3, and it's a 1- compound. So we can still do our, switch the charges trick here. So this is a -1, So we'll have a 1 subscript on the aluminum, and we'll have a 3 subscript on the nitrate. The whole nitrate, you have to put the brackets or parentheses around the whole thing. This is one species, so there has to be 3 of them. So the answer here is actually 3, where we have 1 aluminum and 3 nitrates overall. Right, so I have the nitrate, which in itself, that species is NO3, and then there's parentheses around it. There has to be 3 of them because each of those nitrates has a -1 charge. We need 3 of them to cancel out the aluminum. Okay, so next, copper 2 nitrate. Nice thing about transition metals and variable charge is that they straight up tell you the charge, so that's kind of nice. So here it says copper 2. So that means my cation here is copper 2+. So this will be useful for when we need to figure out how to cancel out those charges to get our neutral compound. And then we have nitrate again, so NO3-. Okay, so we need to combine these 2 species to become neutral. So I see here copper has a 2+, so I need 2 nitrates in order to cancel that out. And so yeah, that's our answer right here. 1 copper, 2 nitrates. All right. Okay, next, iron 3 hydroxide. Again, it's kind of nice when it's a variable charge because it tells you the charge is there. So our cation is iron 3+ because it has a 3 Roman numeral. Hydroxide is one of our other polyatomic anions. Hydroxide is OH-. So we can go ahead and do the subscript switching, charge subscript switching. But remember, this whole hydroxide goes together. We have to keep it together. So our answer here, since there is a 1 charge or a -1 charge on hydroxide, there's only 1 iron. And since there's a 3+ charge on iron, there needs to be 3 hydroxides. And I'm going to put that whole thing in parentheses. So that would be our answer. Writing it like this without the parentheses, this is incorrect, because what you're saying is that there's only 1 oxygen and 3 hydrogens, but when you use the parentheses, you're saying that there's 3 of the OHs together. So together there are 3 oxygens and 3 hydrogens. So this second one that I wrote is incorrect. All right, and so our answer here is number 3. Keep using different colors. All right, last one, tin 4 hydroxide. So I will just give you the answer here. Hopefully you can get that yourself. So it's kind of, we just use the same steps as the previous ones. All right, and I think one more learning check. So let's match each of the formula with the correct name. So I'm just going to give you the answers right now, and hopefully, on your own time, you can go through this and get those answers and make sure that they're the same as what I'm getting right now. All right, so I see that they're all magnesium. I'll just walk through it, I guess. They're all magnesiums, and what's different is the anion. So I just see 1 sulfur. That's monoatomic, so that means it's sulfide. So I see that right here. Ooh, magnesium sulfide. Sulfate, that's one of our polyatomic anions, and I know that's SO4. SO3 is also one of our polyatomic anions. That's SO3. So you see kind of how what this is, it's trying to instruct you to see the difference between monoatomic anion, so in this case just sulfur, versus sulfur within a polyatomic anion, in this case sulfite and sulfate, which are different, and those are listed on the handouts. All right, we can do the same thing with chlorine. So this one's a little bit trickier. So we have calcium in all of them, so we don't have to worry about calcium. We're kind of just looking at this ending here. We have ClO3, 2 of them, ClO, 2 of them, ClO2, 2 of them. So I'm only looking at what's inside the parentheses because that's going to tell me the name, the proper anion name to stick on the end of it. So if you look at your handout, you know that ClO3 is chlorate. So this is calcium chlorate. If you also look at your handout, ClO2 is chlorite. And then finally, just ClO is hypochlorite. That's the active ingredient in bleach. All right, so that is naming ionic compounds. So in the next lecture section, we will compare ionic compounds versus covalent compounds. We've only been talking about ionic. Now let's move on to covalent. How do we identify those? How do we name those?